So today I'm going to talk about the harnessing disorder for photonic applications. So first, maybe when you see this, a title, you'll feel surprised. Most of you, including myself, we all like order, right? We want everything is in order. So why I'm going to talk about disorder, right? Why disorder could be useful. So now let's compare order to disorder. So let's consider order system, right? Let's consider like a periodic array of particles. They all have the same size. So now in this case, there are only two parameters we can adjust. One is the size of the particles, one is their spacing. So that is for order structure. Now if we consider disorder structures, now we can really introducing variation in the size of the particles, in the position of the particles. So then we have many more possible structures we can have, right? So that gives us many more opportunities to make things that we wish to have. That's why typically if you see people do inverse design, try to design the device to have some particular function, very often this nonlinear optimization will give you a structure that look more disordered than ordered. That's just because we have many more, disordered structures that will allow us to really, design, to really get some particular function. Okay, so that is basically why we like to have disorder, because we have more opportunities, right? But then you say, well, what disorder can do? We know that for traditional optical elements, right? We try to, for example, lens, mirror, wave plate, or like a spectral filter, they were designed for one particular function. The lens is for focusing light, mirror is to reflect light, wave plate to control the polarization, and spectral filtering to select the frequency, right? So each one has their own function. But now I try to show you that if we're using a disorder structure, the same structure can behave simultaneously as a lens, a mirror, a wave plate, and also a spectral filter. In other words, a disorder system, a single structure can be a multifunctional device. Okay, so then I'll show you how that could be possible. So let's first take an example to say how this kind of like a sugar tube made of all these like disorder particles, which strongly scatter light. How can that be a lens? Because I cannot even see through it yet, right? So what's a typical lens? A typical optical lens is we try to project an object, to a camera, right? We try to do this kind of imaging, okay? And now if I say, I have a disordered medium, okay? So now when the light coming in, it will just go through this, random scattering, okay? And then when the light coming out, if we have, we usually often get this called the speckle pattern, which is this kind of random grainy pattern. It will completely scramble whatever image, whatever object we want to really see, right? So that is really what we say, this completely scrambled. But even though it's completely scrambled, the information is not lost if the scatters are spatially fixed. Because if all the scatters are spatially fixed, this scattering process is deterministic. So that means if they stay in the linear regime, we have a fixed relationship between the input light and output light. So now if we can know this transfer function, then from this speckle pattern, we can recover the information from the light that coming into this kind of disorder structure. So this actually has been indeed used like for people try to imaging through this kind of highly scattering or opaque medium by really measure the transfer function. In other words, the relation between input and output, and then from the speckle pattern, people can reconstruct the image that you want to send through it, because the information is not lost, right? So you can still using this to send the image or try to do focusing. People can do that. So it's like a lens. But then you say, why you want to using this thing as a lens, right? We have a lens working pretty well, that is working well. Why we want to using this kind of multiple scattering, system, which light will go through multiple scattering, complete scrambled. Then we try to descramble them, right, at the end. So now let's try to see what happened to a lens. When lens do this imaging, it's really like, say, it's one-to-one imaging. In other words, one point, the light from one point will be, refocused to another point. So if we see this object, we can see that, it's, amplified or it's a magnified, image. Sometimes it is, inversed. So now if we have a finite camera, so then we can only measure part of it. So in this case, we don't know whether this is a giraffe, right? Because the head, the light from the head is completely missed the camera. The light from the food, they also missed the camera. We only see part of it, so we don't know what we see if we only have a small camera. Now, if we consider we're using a scattering medium as a lens, now if light from this red point, it will generate like a speckle pattern spread over, everywhere, right? If we have another point, the light from there, they will generate another distinct, pattern through the system. So we are going to have many different points. They are going to generate different patterns. So now if we have a small camera, that means that the light from every point will still can get into my camera. So that means that if I'm using some advanced, computational technique, I may still be able to recover the information from many different points because they are all, assembled, and they are all, sampled. This is actually corresponding to compressive, sensing or computational imaging. Is that when they try to using like a mask for, compressed sensing, they're using a random mask, right? So here you can see about where, scattering medium is also like a random mask that leads to this kind of mixing of the signals. So then if we can try to reconstruct this, information, even we only have a small portion, even we measure a small portion of it. So that basically shows one advantage of using this kind of scattering, system as a lens compared to a standard lens there. So this has been used a lot for like, compressive, imaging, or like people call it diffuser camera. So I think I will probably just, stop here for this one. I want to move to the next one, is to show you the random medium can also be used as a spectrometer. So the same structures, you can use it as a lens, but also you can use it as a spectrometer. So that means we're actually doing this kind of multifunctional device, right? So let me just briefly introducing what is a spectrometer. A spectrometer, we all have, many of you have used that, it's a very powerful tool for us to, for example, for, chemical or biological sensing, or for us try to do material analysis, or, categorization of light sources. So when we try to, buy a spectrometer, what do we, usually, consider? We can first, of course, consider the spectral resolution. But we also care is what is the size, okay, and also what is the, the cost, right? So typically, if we want to have a spectrometer with high spectral resolution, it's usually bulky and also expensive. So in recent years, there has been a lot of, efforts to reduce the size and the cost of the spectrometer, but simultaneously, the resolution will also going down, meaning that we cannot have very high spectral resolution. Why is that? If we open all this, spectrometer, we see they all actually operate with the same mechanism. That is, they're basically all using a grating to disperse light, so the light of different color will be directed to different, spatial location. Then they can measure it by, different photodetectors. So that there's a photodetector array to measure the light of different colors. That will give us a spectrum. So now in this case, if we're using the grating to disperse light so that we can measure the spectrum, how we can get a high resolution? So what we need, first, we need a a big grating, which are very fine groups. And next, we also need to increase the separation between the grating and the detector ray. Because if we have two frequencies are very close to each other, and then they will, their diffraction angle is very, close to each other. So only after propagate over long distance, they can be spatially separated and then measured by different detectors. So therefore, the resolution for those, spectrometer typically scales as 1/L. L is the dimension of the spectrometer. That's why for a bigger spectrometer, we can have better spectral resolution. But now, in recent years, people really want to make this so-called chip scale spectrometer, right? So this kind of spectrometer can further reduce the size, weight, and cost. So that will enable many applications for field spectroscopy, for lab on a chip, also for hyperspectral imaging. But in order to do that, we know that if the size is further reduced, then the resolution will really get very bad. So now the question is, how can we still have a good spectral resolution while have a very small footprint? So in order to do that, we cannot use grating anymore, because as I said, for the grating, the resolution scales, as the size. So how can we make it better? To make it better, we replace the grating by a distorted medium. Because now you can see what happens. When the light going through this distorted mediums, it will go through multiple scattering. Okay, so now you can see that they go through this zigzag, path. So that means that before the light propagating in a straight path, that's why we need a long distance between the grating and the photodetector ray. Here we can wrap a very long path, in a very small footprint by this kind of multiple scattering process, right? So that means we can effectively increase the path length so that we can enhance spectral resolution without making a very big system. In fact, the light, when they go through the scattering medium, they not go through a single path. They go through many different scattering paths, and they are all going to interfere with each other, and then that will actually form a speckle pattern. So this speckle pattern will be unique for each wavelength, because if you have a different wavelength, and then when they, all this scattered wave interfere, because wavelength is different, the interference pattern will be different. So that means we can using this speckle pattern as a fingerprint to recover the wavelengths of light. So as I said, this will enhance resolution. So let's consider if light goes through a diffusion in this kind of scattering medium. And then the average path length scales as L squared over LT. LT we call it the transformation path or scattering length. It tells us how long light will propagate before it's being scattered. So, and then this capital L, it is the size of the, of this scattering medium. So you think that compared to the linear dimension L, we can increase the path length by a factor of big L over LT, which means the system size over the scattering length. And this one we can make the much larger, because the scattering length can be only a few micron. Then we can make our system size much larger than a few micron, so we can have a great increase of the average path length, so we can have a great increase of spectral resolution. So in other words, the spectral resolution scales as 1/L squared. So that means if we increase our system size 10 times, we can increase our resolution 100 times, compared to in the grating case, you only increase 10 times, right? So that is a great advantage to make, this kind of using this disordered medium as, to replace grating, to using this multiple scattering to enhance spectral resolution. That all looks great, but what price do we pay? The price we pay is the transmission, because the light transmitted, after multiple scattering, most light will be reflected back. That's why that the sugar tube looks white, right? So most of light will going back, only a small amount of light will going through it. So the transmission is scales as LT over L. So that means if we can enhance resolution 10 times, we're going to reduce the signal 10 times. So that means we can have a better, better resolution, but we have no signal to measure. So that's not acceptable, right? So we don't want to pay this price. So we want to have a better resolution, but we don't want to pay this price. Can we do that? So can we still maintain high transmission, but still have high resolution? So in order to do this, we actually make this a random spectrometer on a chip. So this is actually made on the silicon uninsulated wafer. So this basically is showing our structures. So in the center, we have this half circle. We etch a random array of air holes in this, into the silicon. So they serve as scatters. And then we have light coming in from the base, the center of the base. And then when light coming in, it will be scattered multiple times. Okay. And then you do have a good chance of going back, right? Because the reflectivity will be high. But then in order to prevent the reflection, we actually make a wall, along the base here. That the wall here is actually made of photonic crystal, which is a periodic structure of air holes. So therefore, we have this in-plane photonic band gap. That means no matter in which way the light hit on this, wall, it will be reflected back. Then we remove one line of air holes so that we can have a defect waveguide to couple light into this, disorder system. And after that, light will go through this multiple scattering, and then they'll be reflected, and then they will, they will diffuse forward until they reach the, this hemicircle here, okay, the other side. And there we make output waveguide. So this output waveguide is tapered so that, actually we can couple light, the scatter light through this one here and to the photodetector. And then in between this output waveguide, we have this also photonic crystal layer. So that means if light miss, one of the, waveguide, output waveguide, they will be reflected back into the disordered medium. They go through multiple scattering. Then they will try, they will hit another output waveguide again. So then they can be coupled to the, couple out. Okay, so in this way, we force light to going forward, and even they go to multiple scattering. Okay, so now in order to use this, we have to calibrate this, this kind of mapping between the spectral domain to the spatial domain. That means that for each wavelength, they will generate a unique distribution of intensity over all the photodetectors. And then if we have many wavelengths coming in, then we will each will generate a different intensity pattern. But because they all different wavelengths, they don't interfere. So we just add their intensity patterns together. That gives us a total intensity pattern, which we measure in this photodetector array. Right. So with this, if we write the detector array. The measurement of the intensity here as, a vector. And then this lambda 1, lambda 2 is really the intensity of light at each wavelength, not just the wavelength itself. This is the intensity at each wavelength. And then we can write that spectrum as another column. So they are related by this transfer matrix that give us a spectral to spatial mapping. In other words, each column of this matrix give us the intensity distribution over all the detectors for each wavelength. So after we calibrate it, then we can recover the spectrum. Because then for any unknown spectrum, we measure the intensity pattern. And then we can recover the spectrum by times the inverse of the transfer function. But the inversion, of a matrix not always, well defined if we have noise. So alternatively, we can using nonlinear optimization technique to minimize the difference between the measured intensity pattern and the product of the transfer function times the spectrum. So with that, we can recover many different types of spectrum, either a broadband spectrum or a multi-line discrete spectrum. The red curve is what we measure using this kind of standard, like spectrometer, and the blue one is what we recover using this random spectrometer. So what spectral resolution we can get? So for this small one, which is this disordered structure, is occupied this half circle of radius 25 micron. The total size is 50 by 100 micron. We are able to separate the two lines, two spectral lines with the spacing 0.75 nanometer at this wavelength 1500 nanometer. Okay, so that means we can really achieve this sub-wavelength, a sub-nanometer resolution with this just a very tiny on-chip spectrometer. So, then you say, okay, fine, you can do this because we can also have fairly high, sensitivity, and we have, this kind of broadband enhancement of the spectral resolution. What are the other advantages? The other advantages is that compared to the traditional spectrometer using grating to disperse light, there the spectral to spatial mapping is 1-to-1. In other words, one wavelength will be mapped into one spatial location, right, through this grating. That's why we, each detector will measure single wavelengths. Again, so if we only have a few detectors, then we cannot measure, for example, here lambda 1, because lambda 1 will never reach any of the detectors. So information will be lost, right? So now if we're using this random medium as, to replace the grating, now this mapping is complex spectral to spatial mapping. In other words, every wavelength will be mapped to all detectors, but they are going to have a distinct intensity pattern that can be used as a fingerprint to recover all these different wavelengths. And the advantage is, again, if we have only a small number of detectors, we can still recover the information, because different wavelengths will always reach the detectors. Why this is very important for on-chip spectrometer? Because for typical grating spectrometer, if you want to measure different wavelengths, we usually have to rotate our grating, right? To rotate the grating so we can go to different wavelengths. But here, if you make it on-chip, if you etch the grating in a wafer, you cannot rotate it. But here, if we do not rotate it using the disorder systems, the light will always hit on the detector, no matter what is the wavelength. So this will allow us to, to use the same structure to measure the spectrum for very broad, spectral range. That's the advantage compared to a grating spectrometer. Another advantage is that, we no longer have this free spectral range for standard, grating spectrometer, which means that for standard grating spectrometer, for one wavelength, say the first order diffraction go to one particular direction, then half of this wavelength, second order diffraction will go to the same, same direction. So this will, cause ambiguity. That's why that limit what is the spectral range we can measure so that's we call the free spectral range. But for disorder systems, we remove any possible symmetry, any possible degeneracy. So if you have two distinct wavelengths, their speckle pattern, will, very unlikely to be the same. In other words, it's just like, there's no, two persons have the same fingerprint. It's very hard to have two wavelengths, very different wavelengths has exactly the same speckle pattern. So therefore, we no longer have this free spectrum range. We can really distinguish many different wavelengths using the same structure. So let me try to summarize the first, part of my talk. I talk about this random spectrometer. So why it's good to using disorder medium? We can have small footprint. We can get a fine spectral resolution. That's because we can use this multiple scattering to achieve non-resident broadband enhancement of spectral resolution. Because in principle, you can say if you want to trap light for a long time to enhance spectral resolution, I can also using a cavity. We can also do that. But the cavity only can trap light for particular frequencies because cavity has a resonant frequency. For any non-resonant frequency, you don't see this enhancement. But for a random structure, multiple scattering occurs for any wavelengths. So therefore, we can have this kind of broadband, non-resonant enhancement of the spectral resolution. Furthermore, we can also, as I said, eliminate the free spectral range. That allows us to have a very broad frequency, operation, range here. And also this kind of system really compatible or suitable for compressive spectroscopy. Okay. So I cover passive device like a lens or spectrometer. I tell you why disorder could, enhance the performance. Now I'm going to do the active device. So I'm going to talk about a random laser. Oops, sorry, there was a typo here. So basically, by introducing disorder into like a laser system, what we try to do is we try to suppress the coherent artifacts. Then we can using this for full field speckle-free imaging. So I think many of you have used laser before. So what's the advantage of laser? It's very bright, right? It provides directional output, and it's energy efficient, and also it gives us spectral control. We can have different colors, right? That's all great. But you can say, well, maybe we can use a laser as an illumination source for full field imaging, for laser projector, for photolithography, or for holography. But actually, for those applications, laser faces a very severe, serious issue. That is a coherent artifact because of its, very high, because its emission has a very high coherence. So that is the speckle, the laser speckle. In the first talk, I showed you that in the first part, I showed you we can using speckle, for this to make a spectrometer, to using these things for, try to use it. But the second part of my talk, I'll try to show you we want to suppress it. We want to get rid of it. And we can using disorder to get rid of it. Why? You say, well, that's strange. How can using disorder to really, get rid of it? Because we know that the speckle really generated, if you, try to imaging through a scattering medium, or if your object, try to image have some, roughness, light will be scattered, and those interference of scattered light will give us this kind of speckle pattern, right? So that is really coming from disorder, right? Now the question is, can we using disorder to get rid of it? So typically how people do it, right, to get rid of this kind of speckle pattern to really see an image. So typically what they do is they actually using a diffuser, which is a disordered, like medium, and then try to, rotate it or move it. So there are many different speckles will be generated sequentially. Then after average over many different speckle, patterns, then the speckle will be averaged out. Then we can see the image. Then you say, how many do we need to do average? The speckle contrast here, C, scales as 1 over square root of M. M is the number of speckle patterns we are going to average. So that means if we want to have speckle contrast of 3%, we need to average about 1,000 distinct speckle patterns. That will take time. So that means we cannot using this for, like a fast imaging. If we want to have a very, small integration time, this will not work because those things, they had to have a very short integration time for all this dynamic imaging. So then that's why for many applications, people still using like white light to get rid of this coherent artifact. Say those kind of lamp or LEDs, because they don't generate speckle, because they have a low coherence. So if we consider all the illumination source for full field imaging, so we can consider that actually usually what we care. We care, how bright it is. That's really described by this photon degeneracy, or we call it spectral radiance, and also the spatial coherence. That is the other parameter we care. Because as we said, for thermal light or for like lamp or LED, they don't have any coherent artifact because of low coherence, but their power is low. So that means if we want to imaging through like some lossy medium or scattering medium, we don't have enough power, Or if we want to do, very fast, imaging, very short integration time, we also don't have enough power. Laser and the superluminescent diode, on the other hand, they can have very high power. That's great. But on the other hand, they have good coherence. So therefore, they have this coherent artifact, like this speckle noise. So what we really want, we want something that, as bright as a laser, but has a low coherence like a lamp, so that we can, really, have both the brightness and also the low coherence to avoid the coherent artifact. So the question is, how can we do that, right? So typically, we know for a laser, they have a gain medium and they have a cavity. So here I plot the simplest, laser. Just cavity made of 2 mirrors. So when we pump the gain material, it will emit light and also amplify light. And this cavity made of these 2 mirrors will bounce light back and forth between these 2 mirrors. That will increase, like this path length of light in the gain medium. Every time light goes through the gain medium, they will be amplified more, right? So that will increase the amplification, and a small amount of the light will be transmitted through the system. So those lasers usually, it's very efficient. It's very bright because it's based on stimulus emission process to amplify light. But on that end, they have a high coherence. So then typically, as I said, people using a moving diffuser to reduce the coherence, right? So to avoid the artifact. So if you see what we're doing here, we first try to make a good laser, meaning a laser with, with good coherence. Then we try to destroy it. We try to destroy the coherence. So rather than doing this, why not just put this disordered diffuser into the laser cavity? And then we can just, remove the high coherence from the beginning. And then in this way, we don't have to first make a coherent laser, and then we try to lower lower the coherence. We can just do it in one step. So then you may say, well, you probably, when you put the diffuser inside the, the laser cavity, you probably will, reduce the coherence, but probably also kill the laser, right? Can it still laze, right? So if we only put a few scatters in this laser cavity, it will not, because the light can be scattered into other directions. If they'll be scattered into other directions, that will introduce an additional loss, and that loss will increase the lasing threshold. So that means if you put in more scatters, eventually the laser will stop lasing, right? But that's not true. If we put in many, many scatters into this gain medium, so then what happens? When the light was emitted, if we pump the gain medium, it will still emit light. Now this light will be scattered multiple times, by all the scatters. So they go through this kind of random walk, right? So this will increase the path length of light, inside this gain medium. So as the light propagating in this gain medium, they can be amplified through the stimulus emission process, right? That's just like what the mirror is doing, is try to trap light in here to have more amplification. Here, just using the multiple scattering, we can increase the path length of light inside the gain medium, so the light has more chance being amplified, and then they can laze. So that means if we have a lot of scatters into the system, we can actually get the system laze even without the mirrors. So that's why this kind of laser we either call a random laser or mirrorless laser, because we're using this disorder-induced light scattering to trap light for amplification. Okay, so that's is called a random laser. And this kind of laser can have a low spatial coherence. That's basically, we did this Young's double slit experiments. It's very simple to show. We have just like a dye solution. Then we put in some scatters like zinc oxide nanoparticles. Then we excite the dye with the second harmonics of a YAG laser. Then the random laser emission will coming out. We project into a 2-slit, then try to measure it in the far field. In the far field, there's no fringes. That means that we have no, we have no coherence here. So this one allows us to have low coherence because this random laser allows, independent lasing in many different spatial modes. Each mode will generate a distinct speckle pattern. So because they're incoherent with each other, we add all their intensity pattern together that will reduce the spatial coherence. But this summation is not sequential like we are using a rotating diffuser. This summation is in parallel, so that's why we can have very short decoherence time that allow us to do very fast coherent imaging. So this basically we show that if we're using the random laser, try to imaging an Air Force, test chart, go through a scattering medium. If we're using helium neon laser, we see a lot of speckles. We don't see any image there. But if you see using a random laser as an illumination, we can still see the image here. Okay, even though the contrast is really getting lower. Actually, there's so the reason why we can do this is because let's consider a lens. We said before, we try to imaging like 2 point A and B to A prime and B prime. If we have some scatters, the light from A will go to B prime rather than A prime. So then it will combine with the light from B to B prime. So now the question is, how do we add the light coming from A and B? If the light illuminating A and B, they are coherent light with each other, we have to add the field from these 2 points. When we're adding the field, then we have intensity, which is field squared. We have interference term. That interference term will depend on the relative phase between these 2 fields. That will generate this kind of noise or this kind of speckle. But if we illuminate this with a random laser, which is spatially incoherent, then the light from A and B are incoherent with each other. So in this case, we're adding the intensity together, not the field. So then all this interference effect will be gone because the scatter light is much less than the original light. So therefore, we can have we can still see the image. And this actually has been used by a German group using this random laser as an illumination source for time-resolved microscopy, because they can just generate a very short pulse as a well-defined time to illuminate the scene, and then just use try to record some dynamic process with only 10 nanosecond recording time. Even with such a short time, the random laser emission is already bright enough to give you a signal, and also it's already decoherent so that we don't have any speckle noise. Okay, so let me summarize the second part. I showed you that by introducing disorder into a laser, we can still make a laser working, but it's called a random laser. It has a very different property from a conventional laser. It is, even though it's it combines the high brightness of the of a laser with a low coherence of like LED or thermal light, so that allow us to do this full field speckle-free imaging using this kind of random laser. Okay, so this I just give you like two or a few examples, right, from to show you why disorder will be useful for photonic applications. We can use why we use that for lens, for spectrometer, for like for a laser. There are many other applications. For example, people have shown the disorder structure can be used to make polarimeter, faceplate, kind of wavefront sensor, and also can be used for reservoir computing, random projection, and also for cryptography and random number generation. So this kind of disorder structures can be used for many different applications because they have many different choices, right? So that's why you have a lot of opportunities there. So you say, I try to convey to you that why we want to harness disorder. First of all, disorder structure is very easy to fabricate. They are robust and they have low cost. But in order to using disorder structure for photonics application, we also have to combine with computational techniques like compressed sensing, machine learning, right? So, so in this way, we can shift the cost from hardware to software. In other words, we're using some very sophisticated software or this kind of computational technique combined with some very simple hardware, like this disorder system, that will make, multifunctional device with low cost. Because we know the software cost usually is going down very quickly. If we can lower the cost of the hardware using the disorder structures, then we can really make the entire system low cost and also multifunctional. In addition to harnessing disorder, we can also engineering disorder, because instead of using fully disordered system, we can also introduce either short range order or long range order to the system. Then we have a huge parameter space for us to explore for different photonic applications. Okay, so I think with that, I'll stop here. I first like to thank the people, my former student and postdoc who has done the work which I show you today. I also like to thank my longtime collaborator, Professor Michael Choma at the Yale Medical School, and the funding also from NSF, NIH, ONR, and FOSR. Finally, thank you for your attention.
Okay. So thank you very much. Thank you very much for Professor Cao's very inspiring talk. So it's well, personally, I find very exciting. I'm sure that the audience will echo myself. And so now will be the questions and answer time. So so either you can type it in the chat box, so such that I can read out the question, or if you find it's a more you prefer to ask yourself, you're welcome to unmute yourself and ask the question. So because since we have hundreds audience, so probably will be may take some time to, well, but anyway, that just let me know if you want to ask any question. So. Okay, so I try to read the questions from Yunchen Chen from page 28. So the question is it on page 28? Right.
Yeah.
So the question is about, is it necessary for the output spectrum of the different wavelengths to be mutually orthogonal, or there should be any other condition? Thank you.
So the question is that in this case, all these different speckle patterns, they are not completely orthogonal, but they are uncorrelated. In a way that if I see the correlation between these two intensity patterns, their correlation are fairly low. That's how we can distinguish different wavelengths. If the two wavelengths are very close to each other, if they generate exactly almost the same speckle pattern, then we cannot distinguish. They don't have to be orthogonal, but they have to be significantly different.
Mm-hmm. Right. Okay, thank you.
Mm-hmm.
So another question that's it's from Danica Zhong. That's the question is how to generate different patterns through the random laser.
Mm-hmm. So so this random laser, all these different patterns are generated by the the spatial distribution of the scatters inside the disordered medium. Okay, and actually in this case, because we don't need these scatters to move around, because we're using a short pulse, so they are kind of during the short pulse, the scatters almost the same here. So they have some configurations, some random configurations. That configuration will generate all these different intensity patterns. Of course, they can you have a different random medium, there were different intensity patterns, but we do not care, because at the end of the day, we just want to have many distinct, many different ones. So when they add them together, we get rid of all the coherent artifacts.
I probably have a follow-up question, because I also have a question is about about the truly randomness, or we talk about the pseudo randomness, just like what you mentioned. For example, the example we just used it. So you shake the die, or like have some kind of motion, so that changed the random pattern already, right? So yeah. Is it like some kind of like, I don't know, optimized random pattern that will help you to serve the various function? For example, spectrometer, would that be like kind of a truly optimized random pattern that would serve the purpose?
Yeah, that's a very good question. Actually, I didn't get into the detail, right?
Oh, okay, sorry.
So let's try to see why the partial order could be useful, right? So I showed you before is that if I have light coming in, this will have a disordered medium, right? And then they couple in, into all this waveguide to the detector array, right? So you see that I try to using a wall here to prevent the light reflecting back.
Right.
So what happened is that the light can scatter out of the plane. Mm-hmm. That is a loss, right? So how I can get rid of this loss? We actually not make a random structure, but we make some, short range order, we call the photonic amorphous structure, or we call this, this introducing short range order, long range disorder, or this is a long range order, short range disorder, like this golden angle spiral, spiral lattice, like those structures, by control the spatial frequency spectrum of these things here, we can see greatly suppressed out of plane scattering loss. There's only the loss here because of this, like the impedance mismatch when the light goes in, that can also be, suppressed. But here show that out of plane scattering loss can be dramatically reduced by introducing certain degree of order into the disorder system. So indeed, introducing some degree of order for some particular application could be useful.
Right. So I think there's another follow-up question by Zhulin Huang. So thanks for your impressive speech. And one question is still on page 28, specifically how to improve the difference of the transmission function. How to improve the difference of transmission function.
Yeah. So so typically for this, so there's a wavelength difference. So typically so when we scan the wavelengths, right? When you're moving the wavelengths, like for certain, like delta lambda, then the speckle pattern will decorrelate. So if I say if the spacing like delta lambda is a 0.1 nanometer, then these two patterns, the correlation would be reduced to say 50%. Then I can recover that. Actually, people even using machine learning, they can even recover much more. Even they distinct by 10%, they can recover. But let's just say this two pattern has to be different by 50%. I can recover it. So what determines this kind of spacing of the wavelength to have 50% decorrelation? And that depends on how strong the scattering is. In other words, is proportional to the length over the transformation path. If I can increase the scattering or increase the size of the random medium, I can make this kind of line width much narrower. So in other words, I can move a little bit, then this speckle pattern will be different. So that's how we can increase the spectral resolution, is to try to enhance the scattering.
Right, I see. Thanks. So another question is from Professor Han Zhang, and asking about like for the imaging. So can we use the speckle pattern for retrieving the depth information?
I see. Yeah. So if you can make the speckle pattern different at the different axial directions, and then when they coming back, they will be encoded by different speckle pattern, and then they can be recovered.
Right, I see. Well, kind of follow-up question, because the speckle, or in the sense, the scattering itself is highly dependent on the wavelength as well, right? So does that mean such kind of spectrometer is also highly dependent, or any kind of spectrometer is highly dependent on wavelength? But I think this kind of spectrum is highly dependent on the scattering phenomenon.
Yes, it is highly dependent on the scattering phenomenon. So that's why. But basically we can design it. So you can design it so to the scattering structures to make it highly sensitive to the wavelength. That's what we want to do here. But of course, you can have also other things which you don't want to be very sensitive to wavelengths to other applications. I didn't get into the detail. Actually, this speckle pattern not only can tell you the wavelengths, they can also tell you the polarization, because polarization state will also change the speckle pattern. So you can make spectral polarimeter. You can simultaneously measure spectrum and the polarization. So you can do many, or people using this for hyperspectral imaging. You can measure simultaneously the spatial location and also the spectrum, because different spatial location, the same wavelengths can give you different speckle pattern.
Thanks. So one question is actually from my students of Cao Hui, and so asking about, is it possible to use an external optical force to change the scattering media pattern? For example, if increasing the laser power exciting the particle, so particle change the position or stay in static. So the speckle pattern probably can be designed or also adjust.
Exactly, that's a very good question. Yes, we can adjust the tune the structure of the disorder mediums, and then using this to adjust this output speckle pattern. Indeed, yeah. Right. Actually, people using this like a liquid crystal, which is also scatter light. And then you can also using either electrical, signals or thermal or many other things to change the scattering configuration.
Well, kind of follow up on that question, would that be, well, for sure, it depends on your application. But for spectrometer, if you look for some kind of highly doable device, but over time, the speckle pattern actually kind of change it, just like what Cao Hui asked about, like the optical force and all those things, you change the speckle pattern over like kind of a period of time. So that probably the thing that will be another issue. Is that, do you see that?
Yeah,
right.
Yeah. For spectrometer, I would thinking that's why we try to make it on chip. Because if you make it on chip, your scatters are everything on chip. That's much more robust. Right? The only thing can change is temperature. But for those chip, you have this kind of packaging which you can get from SOAR lab. They can keep the temperature 0.01 degree. So you can stabilize the temperature. The main thing, if you fix all the scatters, everything here, at the end of the day, what matters is only the temperature drift. Or you can calibrate your device for different temperature. You can store everything in the computer. Then you can using different lookup table for different temperature the system is operating.
Right. Okay. Thank you. Okay. So questions from Cheng Li. That's very great talk. Thanks for your presentation. And for the spectrometer on the chip, so that he's wondering that if the photonic crystal on the chip have the same lattice constant. So that's maybe the slides with a SEM image which show like the structure on the SOI.
Yeah, that is a photonic crystal structure.
Right.
Can you see it?
No, I'm saying that with I think it's they're asking about this. Would that have the same lattice constant? So which is, I assume that's the case.
Same lattice constant, you mean everywhere? Is that, I think maybe the question is that, well, I don't know. Maybe it's that, if we have a photon crystal, if we want to use this one for broadband application, maybe the question is, maybe this will not really confine light for broadband. That's a very good question. So typically, if we do that, what do we do? We actually using like a dilute, like lower density of scatters here, very high random structures here. Because that, just like your paint, if you see the wall paint, is the reflectivity is very high, right? Because it's a random, array, a random assembly of scatters. So if we can make a highly, disordered things in here, we can replace the photon crystal with a highly disordered, closely packed things. That will also have very high reflectivity compared to this region, which is a more dilute scatters. So that can be a broadband, confinement.
That's very true. Okay, so another question is from Professor Chang Yun, that's from you. So thanks for your nice talk. For the random spectrometer, so since the transmission is weak and the reflection is strong, so can we just use the reflected light directly?
Yeah, that's a good question. The reflecting light, the problem is that, as I said, the resolution really depends on, how long the light can trap inside the system, right? So if you see the transmission, typically the light has to stay there for a long time before they can go out. But for reflection, the path lengths can be fairly short. They can just, after like a few scattering, they can just get out. So so in other words, if you calculate the average path length of light that's reflected, that is significantly shorter than the average path length of light transmitted through a disordered system. Because if you want to transmit it, you really go through all the things, right? But for reflection, you may just reflecting from the first few layers that can already reflect most of light back. So if the path length is shorter, then the resolution will be worse for the reflected light compared to the transmitted light.
Okay, thanks. So the question from Dian Yang, it's asking about, could you talk about using the multi-mode lasers for illumination? So what are the requirements of their wavelengths and the number of modes?
Okay, so when I say the multi-mode for illumination, I think about I talk about the multi-spatial modes, not different wavelengths there, because I try to tune the spatial coherence by tuning the number of spatial modes, not number of frequency modes. Why this will be useful? Let me give you one example. For example, for photolithography, right? People using excimer laser, which is a very narrow bandwidth. That's a very high, temporal coherence. So for single wavelengths, if I want to get rid of the speckle noise, then I can only play with the number of spatial modes, not the number of spectral modes, because my laser is just very narrow. So therefore, here when I do multi-mode, illumination, I try to make many, spatial modes, not spectral modes, and those modes they should really each of them can generate a distinct pattern, like what we showed here. is that like that. So this is spatial mode, not spectral mode. That's why this technique can work for, regardless of what is the bandwidth of the laser.
I see. So I got one question is actually that kind of go back to at the beginning, you're talking about using a single device can perform like multi-function, right? So here pretty much show it like the few things like the passive device using as a spectrometer. So, but do you feel like there's what will be your true vision that can using design such kind of device to make it like even more like function can be performed by just single device?
Yes, that's what people have done. So we using design, like say for hyperspectral imaging, that means using as a lens and also as a spectrometer. People doing this for spectral polarimeter, simultaneously, the polarization and also spectrum. So indeed, people have, you see what good for this disorder system. They're connecting the degree of freedom in many different domains: spatial, spectral, temporal, polarization. They all entangled. So they form this high dimensional matrix. So you just, for different application, you just, project into different domains. You can do this mapping between spectral to temporal. You can do this mapping between, like, say, the spatial to the, to the polarization to spectral. So you can do many different things in there. That's why people indeed have shown this things here. For example, I didn't get a chance to talk about the lens and the spectrometer, but people indeed show the hyperspectral imaging using this source, which combines.
Wow, very good.
That's really multifunctional.
True, great. Okay, any questions from the audience? One more thing that's, so if we can make the particle vibrating at a frequency, like via this ultrasound, so the speckle can also be modulated in the temporal domain. So is that would that, I don't know what I mean, but is there any attempt in the random laser?
Right. I think people try to do something shaking some granule things, try to make a random laser with that. I think there was a paper by Claudio Conti published in PRL maybe a few years. I mean, I forgot when was that. Yeah, at least 8 years ago, maybe. Indeed, you can using that also to make a random laser. Yeah.
Right.
And also people try to using that for detection some motion. Yeah.
Good. So one question from Li Mingsheng, that thanks for your amazing talk. That if the laser illuminates the time-varying scattering media, so that the transmission matrix could be time-varying. So do you think is that still possible to retrieve the information, like via for example, the compressed sensing method?
Yes, that's a very good question. So I think people have shown that if they're using machine learning to train a few diffusers, right, to find this in here, then when they have a new diffuser, it still works. So that's not really time varying, but in some way you can learn things from some disorder configuration, and that can be applied to some other disorder configuration. So that has been shown.
Thanks a lot for Professor Cao's impressive talk.